And lastly, we have Professor Xinwen Fu from University of Massachusetts Lowell talking to us about implementing device drivers within trusted execution environments.
Hello. Good morning. I'm very happy to come here and present our work, LDR secure and efficient Linux driver runtime for embedded TE systems. So this is a collaborative work between Southeast University of China, Anhui University of Technology of China, and University of Massachusetts Lowell. So my name is Xinwen Fu. I'm a professor at the School of Computer and Information Sciences at UMass Lowell. The students cannot come here because of the visa issue. That's why I'm here for the presentation. So in this paper, we are concerned with the trusted execution environment. So as we know, the trusted execution environment is a secure execution environment for sensitive applications. So here I show you 4 TE applications. So you can see here, we may use TE for authentication through Touch ID and Face ID. And the TE can be used to support the DRM protected video streaming. It can also be used for performing mobile payment, right? So normally, TE is made compact to reduce the attack surfaces. However, you can see here, in some of the applications like Touch ID and Face ID, we need to actually support device drivers inside of the TE. The size of the device drivers may endanger the security of TE. So this is the problem we try to address, how to support device drivers inside of a TE. To understand our solution, so we need to understand the architecture of a TE. So in this paper, we focus on the ARM TrustZone. This picture shows you the, the architecture of the ARM TrustZone. So ARM TrustZone has 2 worlds, normal world and secure world. So normal world normally runs the rich operating system like Linux, and the secure world runs a compact secure OS. So you can see in the normal world, right, we have normal applications which may use the Linux device drivers to access the actual normal device. And in secure world, we have the trust application which uses the TE native device driver to access the secure device. So the problem here is TE normally has a poor device driver support. And you may think, OK, we can just actually port the Linux device drivers into the secure OS. The problem is, how do we do that? And so in this paper, we try to answer the question, how do we smartly reuse existing Linux device drivers inside of the secure world for security and for efficiency? And so there are already works supporting device drivers inside of a secure OS. So normally, people actually run Linux device drivers inside of secure world in a sandbox for the purpose of security and to reduce the size of the trusted computing base. But there are still problems here. The problem is, a Linux driver may need a lot of dependency functions. And so how do we actually, support those dependency functions inside of the secure OS? So we have 2 options, which are very intuitive. The first one is, OK, we can just actually trim the Linux kernel and port the Linux kernel into the secure OS, right? And the second option is, OK, and we can actually use a function reduction. Means every time the Linux driver inside of the secure world wants to use, a dependency function, and this function call will be redirected into the normal world, which has the dependent function, which has the environment to run it. The problem of the 2 intuitive options are obvious. So for option 1, Linux kernel porting, you still need to trim the Linux kernel. You have to port everything into the secure OS. That's not easy. And also, you increase the TCP base a lot. For the option 2, for function redirection, means every time your driver needs a function, you have to actually perform the word switching. The word switching incurs a lot of overhead. And there are also security issues here because now you depend the normal world for all the driver functionalities. So we want to actually address the issues and answer the questions and solve the problems. So here are two problems we were thinking about and to try to address all the problems here. So first, are all driver functions needed for I/O support inside the TE? So if we're able to actually remove some of the functions inside of this driver, we may reduce the number of dependent functions, right? And the second problem the second question we ask ourselves is, do dependency functions need to be provided inside the secure OS or redirected to the normal world needs kernel? So if the secure OS can provide most of the dependent functions, that's good. We can reuse them. And if they cannot, we may actually redirect them into normal world. So we need to find out how actually the needs driver works to actually answer these two questions. We performed a lot of study on these device drivers. And so here is our result about a generic needs device driver model. And so you can see here, right, we look at the user space and the kernel space. In the user space, we have the applications which utilize the system call interface and the needs virtual file system subsystems to interact with the needs device driver, which is in a gray box over there. And in the needs driver, that we have different components. So you can see here we have the virtual file system interface for interaction between the driver and the application. We have other application modules here to work with the subsystem, and also particularly we have the initialization and the configuration part to initialize the needs device drivers to set up the state variables, including device information and the kernel objects. And also the needs driver needs some of the level functions to work for memory management and I/O. Okay, so now we understand how needs driver works, and now let me present our approach, a tool and driver-based approach to support device drivers inside of secure OS. So basically, we reuse the needs driver and we create two drivers. One is the normal world driver, the other one is a secure world driver. And so here, the normal world driver is used to assist the secure world driver. So let me first show you what is in this normal world driver. So you can see here, in the normal world driver, we actually revise the initialization and the configuration function so that we can actually transfer the initialized state variables to the normal, to the secure world. So we use actually this way to reduce the number of dependent functions, and then the secure world is going to use those transferred state variables for the secure world driver. And we also actually update, the utility functions so that we can actually receive the secure preferred data from secure world, and because some of the normal world, applications may need such data, and all components in the gray will not run at the runtime. So let's look at the secure world. So you can see here, we remove the virtual file system functions because we don't need it in the secure world, and the secure world doesn't need to interact with the links applications. That's why they can be removed. And of course, we export the I/O functions of the device driver so that the secure application can use the driver to access the secure device. And we also actually update the initialization and the configuration function over there. Oh, sorry. And so here, the purpose here is, we needed to get the state variables from normal world, and we use that for that purpose. And we also update the utility secured stub. We created them, and so that we can transfer the secure preferred data to the normal world for the normal world to use. Okay, so let's look at some details of this design. So the first detail is how do we actually address the issue of driver dependency function support? We find actually a device driver needs two classes of functions. One is called the library functions for memory management and I/O support. The other one is needs a subsystem function for like a clock something. Luckily, we find actually, in our case, the OPT, which our approach is based on, provides most of the library functions. So we actually reuse library functions of a secure OS. And in this way, we can reduce the redirection call into the normal world. And then, of course, if we cannot actually provide functions inside of secure OS, for example, the Linux kernel subsystem function calls, then we just redirect them into the normal world. So this is how we address the driver dependency function support. We don't trust the Linux driver because we really don't sanitize the Linux device driver. And when we run them into in an isolated environment. So basically, we use the ARM domain access controller to build the isolated execution domains. So each driver is going to run in their own domain. They will not interfere with each other, and they will not interfere with the secure OS, because we also create something called the IED call gate. And every time, if there's a dependency call into the secure OS, the IED call gate is going to mitigate the call and try to sanitize everything. And so now let me show you some of the modules we add into the secure OS to make everything work. So we use a driver loader here to load the secure world driver into the sandbox. And then the corresponding, the normal world driver is also loaded into the Linux kernel because we need the data from the normal world driver to initialize our secure world driver. So we also create the driver manager and the session manager to coordinate the secure world driver execution. And as we mentioned, we have dependent functions. So basically, these two will coordinate, and we need secure world functions. Then we just use the IED call gate to invoke those secure world functions. If we need to redirect the functions into the normal world, we'll do that with these two modules. OK, good. So now we give an evaluation. We understand the basic idea. Let's look at how we evaluate our approach. So we use a free-scale evaluation board for this purpose. It runs the Cortex A9. And we tested 6 popular sensors: barometer, magnetometer, accelerometer, ambient light sensor, thermal sensor, image percent unit, and we even test the camera sensor. So here, this shows you how much we actually change the original driver. We show you the 6 device drivers over there, and we show you how we actually change them. And the DL means delete the code, and then we also count the changed code and added the code. So you can see here, so basically, we do need to actually change the original code because we need to remove some of the functions, we need to add some functions, but the amount of engineering effort is manageable. And of course, we care about the performance, OK? And so you can see here, so basically, we try to see if our approach will affect the sampling performance of some of the devices. So you can see here, we really don't actually degrade the sensor performance. We want to see if we create a delay when we try to capture the images. So you can see here, we try to count the delay when we capture 1 image, 10 images, 100 images, and there's really no difference in performance by our approach. And then here, we even perform the video streaming and see how our approach will affect video streaming, this kind of computation-intensive applications. So you can see for both resolutions, our LDR really doesn't impact the performance very much. We also compared our approach with other kind of driver support approaches like driverless and my TEE. My TEE is like using option 2. You can see when the sampling rate is high, my TEE has to redirect everything into normal world, the performance will degrade a lot. So now let me summarize our approach. So in this work, we designed a new tooling driver approach which reuses existing normal world Linux kernel drivers instead of a secure OS. And we designed a new Linux driver runtime so that we can reuse the existing secure OS function for the driver. If we cannot use the functions, and we redirect the function calls into the normal world. And we performed a lot of evaluation. You can see here, right, we don't actually have much overhead. So basically, this is the work, and thank you for your attention.
Thank you, Shinwen. Great, Raj.
Raj Rajgopalan, Residio. In your implementation, did you run into problems of excessive memory consumption inside secure world?
Can you say it again? I didn't hear you.
In your implementation, did you run into the problem of some of these drivers exceeding memory allocations?
So basically, we run these driver inside of the secure world, but we run them in a sandbox. The sandbox is implemented as the acyclic domain, execution domain through the ARM domain control manager. So that's how we do it.
So you did not have issues with memory leaks and things like that?
No, we use the ARM access domain access manager. So basically, each component is in their own domain. The secure OS in its own domain, the trust application in their own domain, and the drivers in their own domain. So we use this IED gate and actually to coordinate out the execution. Actually, everything works very well.
Oh, okay. Thank you.
So the student is pretty good.
Cool.
Hi, I'm Deepak from UW Madison. So my question was about the IED call gate. So usually this call gate sanitize system calls and their outputs. So right now you're sanitizing subsystem functions inside the Linux kernel.
Yeah, so the IED gate was designed very, I think, gracefully. And so basically, in a linking stage, right, we actually have put a table inside that IED gate. The table shows which call site is going to call which function. So the IED gate actually knows how to perform all the function calls. So if it's a secure OS, the IED gate will know, okay, we are going to use the secure OS function. If it's these subsystem function call, then we will redirect them into the normal world. So the offline linking, we did do a lot of work to actually remember which function call will be used by our driver.
Right. So my question was, do you have a sense of what kind of conditions you need to check as opposed to?
Yeah. Yep. So we actually check the control flow integrity. We check the parameters. And so the whole approach is designed for former developers. So when they try to develop their things, they know their stuff, right? And so basically, we give them a choice. Okay, you can use this twin driver approach to do everything.
Okay. Yep.
So we know everything.
Yep.
Thank you.
Yep. Thank you.
Cool. With that, let's thank Shinwen and all the presenters today again.
Thank you.